So just coming in, quiz on Tuesday, test 2 weeks from today. Quiz on Tuesday, test 2 weeks from today. All right, so bones. Um, there is a law that describes how things break, and you might have seen tables like this where it describes how much force per unit area is required to break, say, a bone or whatever. This relationship, I'm not going to give you the actual formula because you won't have any calculations, but there is a relationship between the stress and the strain. The stress here, this is just our force per unit area. So it's a lot like our pressure, very similar to our pressure, although slightly different, but we can think of it in terms of pressure. And then strain is how much does the material deform. All right, so if you apply, say, to a bone, for example, if you apply a certain force per unit area to a bone, there is a certain amount of strain that that bone will be able to maintain, that the bone will actually be able to deform slightly before it actually breaks. Again, just know that there is this relationship between stress and strain. We're not going to do any calculations with it. I'm not even sure they do any in your book with this, but just know that there is this relationship between stress and strain. You might see it in some of your athletic training classes, but we can calculate the force. Say, for example, I think we've had a question like this, but let's say if you weigh 180 pounds, and you stand on one leg. Not sure why you'd stand on one leg, but if you want to stand on one leg, what is the pressure on your knee joint? Or particularly, what is the stress on your knee joint? And the area of your knee joint is approximately half a square inch. All right, is it a 180, 360, 90, or 900? And these are all in PSI, pounds per square inch. Which is it? If you weigh 180 pounds and you stand on one leg, you know, like a flamingo or whatever, what is the stress or what is the pressure? Those are very similar on your knee joint if the area of your knee joint is a half a square inch. All right, let's stop at, say, 50 seconds. 50 seconds. Ask your neighbor if you like. 50. Okay, awesome. B is right. This is just force per unit area, F over A, 180 pounds. That's the total force that actually acts on that knee joint. If you're standing on one leg, if you're standing on two legs, right, you get half that because it's split between the two legs. And then the area is a half a square inch. And you get PSI, 360 PSI, pounds per square inch. Or we could write it more correctly, pounds over inches squared. Same. Okay. Right, that's the end for that chapter. In chapter 3, we're going to look at energy and work. And actually, we're going to stop about halfway, or a little bit into this chapter and go outside. I need some help with a little thing. I'll explain it to you. But we're going to look at energy and work. And then we'll also, in the latter half of that chapter, it's fairly interesting. You might have had classes on this, but we'll look at the use of energy in your body. You know, we'll look at like dietary things with your body, how we consume energy, what the energy comes from in the food groups, look at how our bodies burn energy and stuff like that, energy and metabolism in our body. So I think it's a fairly interesting article. first of all, we just need to get a few definitions out of the way. Define what is energy. So chapter 3 is on energy, work, and metabolism. Energy, loosely defined, is the capacity to do work, or the ability to do work. I'm going to say the capacity to do work. And so we need to define also what work is. Work is a very specific thing in physics when we talk about work. It means that a force causes a displacement. So whenever I have work, I have to have both a force and a displacement in order to have work. I can have forces that don't do any work, like for example, if they don't cause any displacement. So right now, there are forces acting on us, but we're not really moving around, so there's no work being done. The gravitational force is acting on us, pulling us down, but it's not doing any work. However, if I allow the gravitational force to cause an object to move, then that gravitational force is doing work on this object. So in order to have this physics definition of work, you have to have both force and displacement, a force and a change in displacement. So if an object has forces but no motion, there is no work. But no motion, there is no work. Okay? Oh, and let me just take a little aside. I forgot to tell you this. Next week, we do have our... Oh, wait, shoot. No, yeah. So next Thursday, we'll have a quiz on Tuesday. Next Thursday, which is the 25th, we won't have class at all. I'm sorry. I have a teacher workshop, and they get here at 8, and I'm with them all day. So I have these middle school teachers that come in, and it's just the way it is. I'm sorry for that. We'll make it up at some point. I mean, I'm not going to give you stuff. No. We'll just sort of keep going at the pace that we're going, and that's okay. But anyway, I'm sorry for missing class on Thursday. I can't really help it. Okay? So just don't come to class. I'll send you an email announcement on Moodle just to remind you. But don't come to class on Thursday. Like, go do something that's less fun than class. I know. Yeah. What's that? Are you happy about that? Okay. So anyway, no class on Thursday. All right, so if an object has forces but no motion, there is no work. If an object is moving, then it must have had work applied to it at some time. Um, so remember the first law, Newton's first law, right? That there is no net force on an object moving at constant speed. So if I have this object moving at a constant speed, there is no net force on it. So that force can't be doing any work. However, there must have been some force that was applied to it at some point in the past. So that's roughly what that means, that if I have this object moving, there must have been a force that was applied to it at some point. So let me write that word. So, but if an object is moving, There must have been a force at some point. That should be sort of intuitive, hopefully. And if there was a force, there was also work being done. If an object's moving, we can assume that at some point in history there was work done on that object, at some point in the history of that object. All right. Okay, so work is the product. May I go to the next page? Okay. Work is the product of force and displacement. Particularly, it is the component of the force that's in the same direction as the displacement. So this force is actually a component of the force in the same direction as the displacement. All right, so say, for example, I'll draw a picture, but let me just show you this first. If I pull this desk across the floor, I'm applying a force to it, and I'm moving it in a certain displacement. But the direction of the force that I'm applying to it is actually up and in this direction. So what I'm saying is that there's really only one force, or one part of this force, that is causing this desk to move to the left. Because you can imagine that this force, which points up in this direction, that it actually has two components. We sort of talked about this when we did Newton's laws, but there are two components. There's a component that is horizontal, and then there's a component that's vertical. Let me draw it in a picture. So if I imagine that table, I'm pulling on it with a force that's in this direction, and I have a displacement in this direction. I can imagine this force is broken into two parts. I'm going to call this F in the x direction, and this F in the y direction. Now, I don't have any displacement in the y direction, so this force is doing what work? How much work is this force doing? If I have no displacement in the y direction, what work is done by this force? Is it 0 or not 0? It's 0 because the displacement in the y direction is 0. However, this force is doing work because I have a force in the x direction and a displacement in the x direction. So when I say that the work is equal to the force times the displacement, the force and the displacement have to be in the same direction. Or, as we'll see, the force and the displacement can be in opposite directions. But I'll point that out in just a second. That's slightly different. Okay? So, a more general way to say this, and don't get caught up in the cosine function, but a more general way to say this would be to say that work is equal to FD times cosine of the angle theta. All right? All you really need to know about that is that you need to know the cosines of three angles. That the cosine of 0 degrees, that's equal to 1. The cosine of 180 degrees, that's equal to negative 1. And the cosine of 90 degrees, that's equal to 0. You might remember that from high school math, or maybe even here you've had this. But the cosines of these angles describe the type of work that's being done. So for example, this force and this displacement, they have what angle between them? 0, 90, or 180? This force and this displacement, what is the angle between them? They're like going in these directions. What's the angle between them? 0, 90, or 180? It's 0. The angle between these is 0. Right? This would be what? That would be 90. And then this would be what? This would be 180. So you see, if I put those in here, if F and D are in the same direction, this term is equal to 1. If F and D are in opposite directions, this term is equal to negative 1. And if F and D are perpendicular, then this goes to 0. If you don't want to worry about the cosine theta, you can just remember those three scenarios. Same direction, positive. Opposite directions, negative. Perpendicular, no work done at all. Because if they're perpendicular, my force is in one direction, my displacement is in another direction. That's not work. That's something else. Okay? But If you want to think about it in terms of this trig function, that's fine too. All right. Let me give you some scenarios. I'm going to ask you a few clicker questions telling me, is the work positive, negative, or zero? So let's imagine in all of these scenarios, my displacement is to the right. I have an object with a force in this direction. So in this scenario, the force is up and to the right. The displacement is to the right. Is the work being done by this, is it A, positive? Is it B, negative? Or is it C, zero? Is this force doing positive, negative, or no work at all? All right, I'll stop at, say, 30. We're going to do several of these, so keep your clickers out. Be ready. 30. Okay, so in this case, my force, or at least a component of the force, is doing positive work. Remember, I can think about this force broken into two components, and this part of the force is doing positive work. So we would say that that force is doing positive work. So A would be the right answer. Let's say that I have an object that's here, and I have a force acting in this direction, but it is moving in this direction to the right. What is that work? Is it positive, negative, or zero? The work that's being done by that force is positive, negative, or zero. And I'll stop at 15. I'll go on to 20. Okay, good. C is the right answer. It's zero because the displacement is to the right, and the force is perpendicular to that. So, you know, if you want to think about this in terms of in words, if F is perpendicular to D, then the work is equal to zero. Or if the angle theta is 90 degrees, then the work is equal to zero. Let's imagine now that I have a block. My force is in this direction. What is the work being done by that force? I have this block. The force is in this direction. It's moving to the right. What work is done? Is it positive, negative, or zero? Now, clearly, if there's a force to the left, it's moving to the right. There are other forces. But I'm just asking about this particular force. Is that work positive, negative, or zero? Okay, good. I'll stop at 35. Okay, good. B is the right answer. That is negative work. So if F and D are in opposite directions, I have negative work. Can you think about this object? If I pull it across the floor, is there being negative work done to the desk? Is there negative work being done on the desk as I pull it across the floor? That is there a force that opposes the direction of motion? I'm pulling it in that direction. It's going in that direction, but is there a force that opposes the direction of motion? The answer is yes. What is the force that opposes the direction of motion? The frictional force, okay? So the frictional force almost always will do negative work. Let's put that down in words. So frictional forces oppose the direction of motion. And almost always, we'll just say always, perform negative work. Okay? What have we used the positives and negatives to represent in the past? We've used sort of positive and negative values to represent what? When we talk about forces, for example, or acceleration. If we have a negative force, what does that mean? What do we use positives and negatives to reference? Direction. Thank you, Marissa. So, yeah, if I have a negative force, it means it's in a negative direction. But in this case, this is a little bit different. A positive or negative work does not give direction. Okay, in fact, work is something we call a scalar quantity. I've mentioned that. We have two different types of quantities, right? Vectors, which have a magnitude and a direction, a value and a direction. And then we have scalar quantities, like, for example, time, mass, charge. Those are all scalar quantities. And work is a scalar quantity. So what the heck does it mean if I have work that either has a positive or negative value? Well, positive work means that I'm increasing the energy of the object. Negative work means that I'm decreasing the energy of the object. So decreasing, not increasing. And then zero work means that the energy of the object is constant, or the energy is unchanging. All right, so if I push this desk, like if I give it some initial force and make it move across the floor, as it's moving across, the frictional forces are acting upon it, and they're taking energy away from that desk. Right? If I push it, I give it some energy, and then the frictional forces slowly take away that energy, or, in a matter of a second or two. Okay? So if I have negative work, that means that I take away energy from the object. If I do positive work, that means I give energy to the object. And if I don't do any work at all, or ow, as it says there, if I do zero work, that means that I will not change the energy of the object at all. Okay? We have lots of different kinds of energy. One of those is kinetic energy. May I go down? Give you a second. I did this, I'll tell you a little story right quick. It's kind of funny. I did this thing at my daughter's school yesterday, like in her class. I was subbing for her class, and I took these little beads that when you take them out in the sunlight, they change color. You ever seen those? Those little pony beads, I think they're called. You make bracelets and stuff out of. You never made a bracelet out of them? Yes. No. But y'all have, right? You seen them? Know what I'm talking about? You put them on pipe cleaners and you make little bracelets or necklaces or whatever. So, but these, when you take them out in the sunlight, the UV radiation causes them to change color. So I told these second graders, man, second graders, they're so gullible. I told them, we're going to make today a UV radiation detector. And I go, oh, wow, really? And then I pull out these pipe cleaners, like, hey, these are pipe cleaners. I said, no, 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 no. These are special UV radiation bracelets. And so they're like, well, I said, I bought them from a special science supply store. And then we handed out the beads, and like, these are beads. I'm like, no, they're UV radiation detectors. I'm like, oh. And then they didn't believe me, but then I showed them the package, and they actually said that on there. But so they didn't really know what was going to happen. And then I pulled out this black light, and of course that's UV radiation, right? And the beads started changing color. They thought it was going to beep or something, like beep, 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 but then they changed color. They thought it was really cool. Anyway, I thought it was kind of fun. Maybe we'll do that when we get to that. Okay, so let's look at energy. We have lots of different kinds of energy. A big one is called kinetic energy. It's just the energy of motion. The kinetic energy, I'm going to call it K, is equal to 1/2 the mass of the object times the speed squared. This is the mass in kilograms. This is the speed meters per second. You have to be in SI units to get your units to work out right. And I'll give you the units for energy in just a bit. Now, as we said, if you do work on an object, the energy changes. This is something called the work energy theorem. It says that if I do work, I cause a change in energy. And it's a pretty basic and fundamental idea in physics, that if I do work on an object, I will change its energy in some way. Sometimes that's going to be a change in its kinetic energy, or as we'll see later, it can also cause a change in its thermal energy or in its potential energy. We'll see what that means in just a bit. So if you do positive work, then this causes a change in the energy. For example, if I push a car, that is a positive work. I'm pushing it in the direction that it's moving. I increase the kinetic energy. I give it speed and increase the kinetic energy. The units of work and energy. Well, you tell me. Which of these is a unit of work? Is it A, Newton meter, newtons times meters? Is it B, meters per newton? Is it C, newtons per meter? Or is it D, Newton meters per second? Which of these is the unit for work? Is it Newton meter, meter per newton, newton per meter, or is it a Newton meter per second? Which of those is a unit for work? Think back, what is work, right? I mean, how do I find work? And then you can reason out what are the units. How do I find out what work is? Okay, y'all are like all over the board, okay? You know what the units are. How do I calculate what work is? The work is the product of what? Force and distance, right? So you should be able to run with that and figure out what are the units for work. Okay, I'll stop at 105. 105. All right. It is A. Listen, guys, I like to ask these questions on tests, and you'll probably see something like this. You might, where I just ask you the unit for something. If you ever confused about what the units are for something, just go to the formula. So I know that work is equal to the force times the displacement, and I want to know the units for work. Well, I know the units for force. That's the Newton, right? Like the Newton burger. If I wanted a quarter pounder, I go and ask for a Newton burger. And I know the units for displacement. That's my meter. And so my units for work are going to be newtons times meter. So A would be the right answer here. Okay? It's useful to be able to work in your units and think about what the units are and what they mean. Yeah, so it turns out that actually the unit for work is a Newton meter. And a Newton meter is equal to something that we call a joule. It's named after a scientist, so it's capitalized. A joule is the unit for energy. You might have seen joule before in chemistry or some other class that you've taken. It is the unit that we use for energy. Sometimes you see joules in food energies, but more commonly you see another unit for energy, which is the calorie. But a joule is just another name or another unit for the same thing we use calories for. It is a unit for energy. The basic SI units, if I wanted to know the basic SI units for this, it's going to be, well, 1 kilogram meter per second squared. All right, that's a Newton, because a Newton is F equals ma, Newton's second law, kilograms, meters per second squared, And then what else do I need there for the units of a joule, the basic SI units? I'm missing something. What's that? Okay. I also want to know what are the basic SI units for the joule or for the Newton meter. I want to know this is equal to this is equal to what? Well, this is the basic SI unit for a Newton, okay? Because I know that a force, which is in newtons, is equal to a mass, which is in kilograms, times an acceleration, which is meters per second squared. So what am I missing here in order to make this equivalent to the joule or the Newton meter? What am I missing in this expression to make it equivalent? I need another meter, right? Because this is my Newton right here. I just need to add my other meter in. So the basic SI units, that is going down to those three basic quantities, mass, length, and time, are going to be kilogram meter squared per second squared. You could see a question like that on the quiz or on the test, or not. Yeah, I guess you see it on the quiz too, or on the test, just exploring the idea of units. And always return to your equation sheet and look at what the equation looks like, and remembering, well, this is a force, it's a mass times acceleration, work is force times the distance, and you can tease out what those basic SI units are. Okay, one more thing, and then we'll go outside for a few minutes. There's another thing. We'll come to this later, but I wanted to go and introduce it here, called power. Power is work over time, or energy over time. It's measured in what? Watts. So the unit is the watt. 1 watt is equal to 1 joule per second. So our power is this. The unit is watts. And a watt is equal to a joule per second. I had a friend named Power once. Yeah, isn't that strange? Like, that was his name, was Power. It was strange. He came to me one day and he said that he was just really stressed, like, because his boss was making him work overtime all the time. What's that? I thought that was an excellent joke, actually, and nobody got it. Because his boss was making him work overtime. Work overtime. Y'all are so dense. No, that's the stupidest name I've ever heard. Yeah. Okay, so I want to try something. I'm working on this project with this guy up in Philadelphia, and sort of there's this idea that when we walk, that we have this natural pace that we will walk at. And it's a pretty simple model where they describe how you walk, that everybody has a natural stride length and a natural speed at which they walk, because your body wants to use as little power as possible when you're walking at a comfortable pace. And this walking, you can describe your walking by a couple different things. You can describe it by your stride length, like the length of your stride, and then you can also describe it by your leg length. I'm not going to go through the model. It sort of has to do with optimizing the power that you use in your body. How much do you go up and down like this? Because that takes up a lot of power. And how far do you stretch out your legs? Because that also uses up a lot of power, a lot of energy. But the basic idea is that my speed of walking, don't write this down, you're not going to see this again, but your speed of walking is proportional, not equal to, I'm sorry. Your speed is proportional to the square root of d over, d over the square root of L. Where d is your stride length, and L is your leg length. Okay? So what we're going to do is we're going to go outside. I'm going to have you all walk about 50 feet. You're going to do it a couple times because I want to average together your speeds and your stride lengths so we get a good comparison. And I also want you to measure your leg lengths. So as you're waiting, I have a tape measure. I want you to measure your leg lengths. You'll take the tape measure like this. You'll just, first you want to figure out where your leg starts. Your leg is going to start, like if I do it down here, see how my finger moves? That's not where the start of my leg is. My leg is going to start like right about here, so that it's at the place where it doesn't move. So right about your hip, where your hinge of your leg is. You can feel it if you just do this. So you're going to take the tape measure, put it on the ground, and then measure your leg length. Mine's right at about 40 inches. Okay, it's not the inseam. So like if you're a guy and you have a 32-inch inseam, that's not it. You want your length up to where the hinge is on your leg. And then we're going to go outside and we'll walk a certain distance. And I'll have a couple of you. Do you have cell phones? Do you have timers on them? You have a cell phone? Yeah, I don't either. Okay. I won't need a couple people to time it. I'm going to give you all a sheet of paper. We're going to each do it twice. Oh, where's my paper? And I want you to put your name, your height, your leg length, and the number of steps that you take. So as you're walking the 50 feet, just walk normally. Like, don't try to walk cool or anything like that because everybody's watching you. You just walk normally, okay? Please do that because if you try to walk all cool, it's going to mess up the thing. Huh? Was that a snide comment? No, okay. So just walk normal, act like nobody's watching you, okay? Or maybe don't act, just walk normally, okay? And then I also want you to count the number of steps. As you're walking the 50 feet, I want you to say 1, 2, 3. Is that okay? That's a lot to what? No, it won't, Shelby. No, it won't. Okay, so you each need 2 of these, so take 2 and hand it back. You can go and write your name on there and your height. You can just write your height in inches. My friend up in Philadelphia, he did this and it didn't work so well for his students, but he said he thinks that they were just messing around. But y'all are much more serious than they are. Okay? So take 2 of those. You're going to write your name and your height on them. And then, so I'll show you the results of this next time after I have a chance to look at it. But if this relationship is indeed true, if we plot D versus square root of L, this should be a straight line because there's a linear relationship between D and L. So we'll see that next time and see what it looks like. I'll show you the results of that. Okay? I am going to lock the door, and we'll just go out that back door right there. So you can leave everything in here. All right, nobody's going to come in here. If you want to take your cell phone over, that's fine. And if a couple of you could take a cell phone as a timer, that would be great too. Okay? Yeah. Sure. Anybody else need another one? So you know what we're going to do? We're going to go outside. I'll set up a track that's 50 foot long. We'll mark it with these 2 orange flags to mark your beginning and your starting point. Be just a couple minutes as I get that. And then you'll start walking. And then as you're going along, y'all just go ahead and measure your leg length. Okay? It's very important that you measure your leg length up to where the hinge is. So try to find that hinge best that you can. So if you sort of hold like this, you can feel it. Okay? All right. Let's go try this out. Actually, hold on just a sec.